Now, let us start with a new chapter, that is, chapter 3rd, which mainly deals with frequency representation or Fourier representation of signals. To give motivation about this chapter, let us consider a generic case where there is a sinusoidal input or exponential input given to a discrete time system of impulse response h of n. Let the output be y of n in this case. If the full frequency representation of the signal h of n is h of e power j omega, we can represent y of n as h of e power j omega multiplied by e power j omega n. That is, e power j omega n gets scaled and phase shifted by h of e power j omega value at frequency omega. This can generically be applied for any frequency omega. Similarly, in continuous time case, if we give a exponential input e power j omega t to a LTI system of impulse response h of t, then the output of the LTI system is h of j omega multiplied by e power j omega t, where Fourier transform of h of t is equal to h of j omega. So we see that any LTI system for a exponential input e power j omega n or e power j omega t, we can generically represent the output as shown. We will also see that given any input signal x of n, it can be seen as a linear combination of e power j omega n in discrete time domain case, and given any signal x of t, it can be seen as a linear combination of e power j omega t, where small omega or capital omega would be varied. Now, given this, we see that we can generically get the output of the system, that is y of t or y of n, using h of j omega or h of e power j omega, where h of j omega and h of e power j omega are defined as shown. Now, let us look into the frequency representation of the signals. So, we will be making a table here which mainly deals with nature of signal, where we say if the signal is continuous time or discrete time and periodic or non-periodic. We will also write down the type of frequency representation, means how you term the frequency representation. Then finally we talk about nature of the frequency representation. So given any signal, by the nature of it, we will see how we can represent it in the frequency domain, and we will also be looking into the nature of the frequency response. Let us consider a continuous time signal, and let the signal also be periodic. In this case, we see that the frequency domain representation of the signal can be given by Fourier series. Also, please note that the Fourier series coefficients are discrete and non-periodic. Now, let us consider a discrete time periodic signal. Here we see that its frequency domain representation can be given by discrete time Fourier series, and also note that the representation, that is DTFS, is discrete and periodic. Now let us consider a continuous time non-periodic signal. Its frequency domain representation can be given by continuous time Fourier transform, Also note that continuous time Fourier transform of a signal by the nature of it is continuous, that is, it is defined for all frequencies and also is non-periodic. Finally, if we consider the case where the signal is discrete time and non-periodic, its frequency domain representation is given by DTFT, that is discrete time Fourier transform. Also, please note that nature of the DTFT is continuous, that is, it is defined for all frequencies and is periodic. So here we see that depending on the nature of the signal, that is whether it is continuous time or discrete time or periodic or non-periodic, we can give the frequency domain representation as listed. Also please note that the nature of the frequency representation is given in the third column. So here we see that from the given table, if the signal is continuous time, that is it deals with case 1 and 3, we see that the frequency domain representation is non-periodic. That is, we can say that the continuous time signals have non-periodic, sorry, continuous time signals have non-periodic frequency domain representation. Similarly, we can say that discrete time signals have periodic frequency representation. That is given by case 2 and 4. Now, if we consider the periodic signal case, that is covering the cases 1 and 2, we see that the frequency domain representation is discrete. Similarly, we see that for continuous time signal case, the frequency domain representation is sorry. Similarly, we see that for non-periodic signal case, we see that the frequency domain representation is continuous. That is, we can say that the periodic signals have discrete frequency representation and non-periodic signals have continuous frequency representation. From this, we can deduce that if the signal is continuous, let it be periodic or non-periodic, it has a non-periodic frequency representation. If the signal is discrete time, let it be periodic or non-periodic, it has periodic frequency representation. If the signal is periodic, let it be continuous time or discrete time. The frequency domain representation is discrete. If the signal is non-periodic, let it be continuous or continuous time or discrete time signal. Its frequency domain representation is continuous. So we see that depending on the nature of the signal, the frequency domain representation varies and also nature of the same varies. Also, please note that if the signal is continuous time, its frequency domain representation can be given in a generic form using Laplace transform. That is, continuous time Fourier transform is a special case of Laplace transform. If the signal is discrete time, its frequency domain representation can be given by Z transform. That is, we can say that DTFT is a special case of Z transform. We will be talking about Laplace transform and Z transform in the subsequent chapters. So, as a whole, we can say that Laplace transform, Z transform, Fourier series, DTFS, CTFT, DTFT are different ways of representing a signal in the frequency domain, and Laplace transform and jet transform are special are the more generic cases of frequency domain representation of continuous time or discrete time signals, which will be covered in the subsequent chapters. We also see that Fourier series, DTFS, CTFT, and DTFT will be covered in detail in the current chapter. Now, let us look into some of the properties of complex exponentials, which would be helpful while looking into the frequency representation of the signals. The first property is the discrete time complex exponentials which are separated by 2 pi or multiples of 2 pi are identical. That is e power j multiplied by omega naught plus 2 pi k multiplied by n is equal to e power j omega naught, where k belongs to z. Now, the second property is as related to the orthogonality property of discrete time complex sinusoids, which can be written as sigma n equal to 0 to n minus 1 e power jk multiplied by 2 pi by capital N multiplied by n is equal to n if k mod n is equal to 0, it is 0 otherwise. That is the summation from n equal to 0 to n minus 1 for the complex exponential that we have written leads to n if k mod n is 0, it is 0 otherwise. Now the third property is related to the orthogonality property of continuous time complex sinusoids, that is integral t0 to t0 plus capital T e power j multiplied by k minus m multiplied by omega naught t dt is equal to t, that is capital T, if k is equal to m, 0 if k is not equal to m. From this we see that for a given continuous time complex inside, the integration over t0 to t0 plus t is capital T if k is equal to m, 0 if k is not equal to m. Now let us look into the Fourier series representation of the signals. As we have seen before, the Fourier series representation is for continuous time signals and periodic signals. That is, the Fourier series representation that we would be talking about is for continuous time and periodic signals. The Fourier series representation has two types of representation. One is complex representation, other one is a alternate representation. Given any signal x of t which is periodic with period capital T, whatever we are talking is about the complex frequency representation, complex Fourier series representation. Its frequency representation is given as capital X of k, where omega naught is equal to 2 pi by t. We can represent x of k as 1 by t integral 0 to t x of t multiplied by e power minus jk omega naught t. And this is the analysis equation. And the synthesis equation is given as x of t is equal to sigma k equal to minus infinity to plus infinity x of k multiplied by e power jk omega naught t. So please note that for the analysis and synthesis formula that we have written, in case of complex Fourier series representation, the time period is considered as capital T. Now we will look into the alternate Fourier series representation. In this, we consider the signal x of t to be periodic with a period 2t. In this case, the given signal x of t can be written as a0 by 2 plus sigma n equal to 1 to infinity an cos omega nx plus sigma n equal to 1 to infinity bn sin omega nx. Sorry, an cos omega nt plus sigma n equal to 1 to infinity bn sin omega nt. Please note that here omega n is equal to 2n pi divided by 2t. This is the synthesis equation. Now the analysis equation can be written as a0 is equal to 1 by t integral minus t to plus t f of t dt. An is equal to 1 by t multiplied by integral minus t to plus t f of t cos of omega nt dt, and bn is equal to 1 by t integral minus t to plus t f of t sin omega nt dt. So here we see that the formula that we have written for a0, an and bn correspond to analysis formula, and the representation of x of t in terms of a0, an and bn is like synthesis formula. Please note that in case of complex representation, we have considered the period as capital T. In case of alternate representation, we have considered the period as 2t. Now, we will look into the necessary conditions that should be satisfied for the Fourier representation to exist. That is, for the Fourier series representation to exist either in complex form or in alternate form, there are some conditions to be satisfied, which are called Dirichlet conditions. The first condition is x of t is absolute integrable over one period. That is, integral of mod of x of t dt is less than or equal to m, where m is finite. Please note that this integration is over one period. The second condition is x of t has finite number of local maxima and minima in one period. And the third condition is x of t has finite number of discontinuities in one period. So from here we see that for the Fourier series representation of a continuous time periodic signal to exist either in complex form or alternate form, Dirichlet conditions should be satisfied. They are integral of mod of x of t dt should be finite. This is over one period. There should be finite number of local maxima and minima in one period. Also, there should be finite number of discontinuities in one period. If these three conditions are satisfied, we can say that Dirichlet conditions are satisfied. Hence, the Fourier series representation of the given signal or the given periodic signal exists. Also, please note that in case of alternate frequency representation, there are two special cases that can be considered. That is, if the signal x of t that is given is even, then the coefficient a0 is equal to 2 by t integral 0 to t f of x of t dt, and the coefficient an is equal to 2 by t integral 0 to t x of t cos of omega nt dt, and bn is equal to 0. If the signal x of t is odd, then a0 is equal to 0, an is equal to 0, and bn is equal to 2 by t integral 0 to t x of t sine of omega nt dt. Please note that in case of alternate frequency representation, the coefficient a0 by 2 is called DC term. An and Bn correspond to cosine and sine terms. Now let us consider some examples. Suppose there is a signal as shown in the figure, which is a pulse for 0 to pi, and the signal is 0 from pi to 2 pi, and so on. Please note that the signal x of t is periodic with period 2 pi. Then find its complex Fourier series coefficients, that is x of k. We know that in case of complex Fourier series representation, x of k can be written as 1 by t integral 0 to t x of t e power minus jk omega naught t dt. where omega naught is equal to 2 pi by t, where capital T is the time period of the signal, which is equal to 1. Upon substitution, this can be written as 1 by 2 pi integral 0 to pi, because the signal from pi to 2 pi is 0. Okay, let this amplitude be 1, e power minus jkt dt, which can be written as 1 by 2 pi e power minus jkt divided by minus jk, and note that the limits are pi to 0. Upon substitution, this can be written as 1 by 2 pi jk 1 minus e power jk pi. This can further be simplified as 1 by 2 pi jk multiplied by 1 minus. We know that e power minus jk pi can be written as e power minus j pi whole power k, where if where e power minus j pi is minus 1. So this can be simplified as minus 1 whole power k. From this, we see that the complex Fourier series coefficients are 1 by 2 pi jk multiplied by 1 minus 1 whole power k. Please note that here k belongs to z. Now, let us consider another example in which there is a signal x of t that is given as shown, that is, it is a square waveform which has a value of 1 from 0 to pi, and it has a value of minus 1 from pi to 2 pi. Please note that the signal x of t is periodic with period 2 pi. Now we have to find its Fourier series coefficients, that is a0, an, bn, as per alternate Fourier series representation. Here we see that x of minus t is equal to minus x of t. That implies the given signal x of t is odd. We know that if x of t is odd, a0 is equal to 0 and an is equal to 0. From this we can write that bn is equal to 2 by pi, because please note that here the time period is 2 pi, that is 2t is equal to 2 pi as per the formula. So bn is equal to 2 by t, that is 2 by pi integral 0 to t x of t, that is 1, multiplied by sine of omega nt. We know that here omega n is equal to 2n pi divided by 2t, which is equal to n, because 2t is 2 pi. From this we see that omega nt will be nt dt. This upon simplification becomes 2 by pi minus cos of nt divided by n, and the limits to be substituted as are from t to 0. So sorry, this is t is pi. So which upon simplification becomes 2 by n pi 1 minus 1 whole power n. This can be obtained by substituting the limits. So from this we see that for the given square waveform, the coefficient a0 is 0 and the coefficient an is 0. That is, there is no DC term and there are no cosine terms. So there are sine terms present, for which the coefficients are given as bn is equal to 2 by n pi multiplied by 1 minus 1 whole power n. Now let us consider another signal which is as shown in the figure. So here we see that the signal is periodic with a period 2 pi. That is, the given signal x of t is periodic with a period 2 pi as shown. So the one period of x of t is marked. So here we see that x of t is say 1 from 0 to pi by 2 and from 3 pi by 2 to pi, and it is 0 from pi by 2 to 3 by 2. Now we have to now let us consider another example as related to alternate Fourier series representation of a periodic signal. Let us consider a periodic signal f of t with a period 2 pi, which is as shown in the figure. Here we see that the signal f of t is present from minus pi by 2 pi by 2. Its value is 1 and f of t's value is 0 in the range of pi by 2 to 3 pi by 2. Similarly, as before, f of t is 1 from 3 pi by 2 to 5 pi by 2. Please note that f of t is periodic with a period 2 pi. Now find out the terms that would be present in the alternate Fourier series representation of f of t. That is, find out if f of t contains DC term, find out if f of t contains cosine terms, find out if f of t contains sine terms in alternate fs representation. From the given signal representation, we see that the signal f of t is even, that is f of minus t is equal to f of t. From this, we can say that a0 is not equal to 0 and an is not equal to 0. That means f of t contains DC term and cosine terms. Also, please note that as signal is even, bn is equal to 0. So, f of t will not contain sine terms. From this, we can say that in the alternate fs of Fourier series representation of given f of t, DC terms and cosine terms are present and sine terms are not present. Now, let us consider another example as related to complex Fourier series representation of the signal f of t. Suppose the Fourier representation of f of t is, that is, f of Fourier transform, sorry, is f of k. Let a signal f of t has the complex Fourier series representation as f of k. Now, if f of t is real, please find out the value of f star of minus k. We know that f of k, that is the complex Fourier series representation of given f of t, is given as f of k is equal to 1 by t integral 0 to t, where t is the time period of the given signal f of t multiplied by e power minus jk omega naught t, where omega naught is equal to 2 pi by t. From this we can say that f star of k is equal to 1 by t integral 0 to t f star of t is multiplied by e power jk omega naught t. That is, we find out the complex value of f of t and e power minus jk omega naught t individually. But we know that f of t is real. It means that f star of t is equal to f of t. From this, we can write that f star of k is equal to 1 by t integral 0 to t f of t e power jk omega naught t. From this, we can write that f star of minus k is equal to 1 by t integral 0 to t f of t e power minus jk omega naught t. This is by replacing k by minus k in f star k. But we know that this is equal to f of k. From this, we can say that if a given periodic signal f of t is real, in its complex Fourier series representation, f star of minus k is equal to f of k. It means that the Fourier series representation is conjugate symmetric. Now, let us look into frequency representation of discrete time periodic signals, which is so here the frequency representation can be done by discrete time Fourier series. Please note that discrete time Fourier series is for discrete time and periodic signals, and also note that the DTFS by its nature is periodic and discrete. So here suppose there is a signal x of n given, its frequency representation is given by DTFS. Here please note that x of n is a discrete time signal and is periodic with a period n. Then its Fourier series representation DTFS is given as x of k. Please note that x of k by its nature is discrete and periodic. As the signal x of n and x of k are periodic, we represent the same by tilde as shown. That is, a periodic x of n will have a DTFS of periodic x of k. Please note that here omega naught is equal to 2 pi by n. So from this relation, the DTFS representation of given periodic signal is given as xk is equal to sigma k equal to 0 to n minus 1 x of n multiplied by e power minus jk omega naught n, where omega naught is equal to 2 pi by n. So this is a analysis equation. Similarly, the synthesis equation, that is to get x cap fn from the periodic x of k representation can be written as 1 by n multiplied by sigma k equal to 0 to n minus 1 x of n multiplied by e power jk omega naught n. So here please note that as before, x of k is periodic in nature with a period n and is discrete. Now let us consider an example in which there is a periodic signal given as x of n is equal to 1 comma 0 comma 1, where the first one corresponds to the instant n is equal to 0. Please note that x of n is periodic with a period 3. Now as per this example, we have to find the DTFS representation of periodic x of n. We know that for the given periodic signal, the DTFS representation is given as x of k is equal to sigma n is equal to 0 to n minus 1 x of n multiplied by e power minus jk omega naught n. Here we know that capital N is equal to 3, that is the period of the given signal, and omega naught is equal to 2 pi by n, that is equal to 2 pi by 3. Upon substitution, we can write the periodic x of k as sigma n equal to 0 to 2 x of n multiplied by e power minus jk 2 pi by 3 multiplied by n. So for k is equal to 0, we know that x of 0 is equal to 1 plus 0 plus 1, that is equal to 1, sorry, 2. For k is equal to 1, we know that x of 1 is equal to x of 0 multiplied by 1 plus x of 2 multiplied by e power minus j 2 pi by 3 into 2. So this upon simplification becomes 1 plus e power minus j 4 pi by 3. Similarly, for k is equal to 2, we can write that x of 2, capital X of 2 is equal to x of 0 multiplied by 1 plus x of 2 multiplied by e power minus j 4 pi by 3, sorry, 8 pi by 3. This upon simplification can be written as 1 plus e power minus j 8 pi by 3. So here we can write that finally the DTFS representation of given signal is x of k is equal to 2 comma 1 by 2 minus j root 3 by 2 comma 1 by 2 plus j root 3 by 2. So as x of n is periodic with period 3, its DTFS representation x of k is also periodic with period 3. Now let us consider another problem. If x of n is a periodic signal and if its frequency representation is given as dtf x of k, and if x of n is periodic with period n, prove that x of k is also periodic with period n. We know that capital X of k is equal to sigma n is equal to 0 to n minus 1 x of n multiplied by e power minus j 2 pi by capital N multiplied by small n. So for proving that x of k is periodic with period n, we have to show that capital X of n plus k is equal to capital X of k for every k. So this can be done by replacing k with n plus k in the given analysis equation. From this we can say that x of n plus k is equal to sigma n is equal to 0 to n minus 1 x of n multiplied by e power minus j into 2 pi by n into n plus k multiplied by n. This can further be simplified as sigma n is equal to 0 to n minus 1 x of n multiplied by e power minus j into 2 pi n multiplied by e power minus j 2 pi by n kn. But we know that for every small n, e power minus j into 2 pi n is 1. So from this, we can simplify the analysis equation x of n plus k as sigma n equal to 0 to n minus 1 x of n multiplied by e power minus j into 2 pi by n multiplied by kn, which is equal to x of k. From this, we can say that if the signal x of n is periodic with period n, its DTFS representation, that is capital X of k, is also periodic with period n from the above proof. So if the signal to be analyzed in the frequency domain is periodic with period n, its frequency representation is also periodic with period n. So this is in the case of DTFS.